without wasting time, I'll quickly start. Good afternoon, everyone. First of all, thank you very much, Ekta, for creating such a nice platform for technology presentations, so that those technologies should get everybody should get aware about the technologies. Also, technologies always have upgradations and also have improvements. But once it gets presented and used by someone, majority of good technology updates or changes gets happened because of high scale usage. I quickly start with my presentation. So today I'm going to talk on a process or a technology wherein it can enhance the cooking process with respect to not only the process side, but also will also consider the environmental aspect, help in reducing the environmental concern associated with the cooking process. So I will have a discussion technology description in terms of environmental concern associated with the cooking process. What is a dual technology? Why it requires a dual kind of technology, a probiotics and bio-based kind of combination? What is the technology key focus, chemistries and interactions involved in that, and also it will talk on some of the key results, the lab results, the external lab validation results, and also one of case study with one of the paper mill where we have used this product for almost 3 months of the program and the key benefits. So let's start with the cooking process. So pulping, as we all aware, cooking process or the wood pulping have different concerns in terms of having the process side, like some of the concern in terms of the inefficiency, let's say in terms of yield or the quality of the pulp, and at the same time some of the environmental major challenges or key concerns if you look at the wood chips or the breaking chemistry of the wood chips or pulping process, majority of it has the three key chemicals involved in that, that is cellulose, hemicellulose and lignin portion, out of which the pulping process mainly focused on removing the majority of the lignin and part of hemicellulose out of that, so that the cleaned cellulose pulp will go ahead for the further processing for making the paper, along with some of the hemicellulose involved into it. So in that case, what are the inefficient, like when we say the inefficient cooking process, the pulp will have what, so it may have the higher resistance to it, the overall yield may be low, it may have a lesser efficiency for the next stages like ODL stage efficiency. It may have some of the challenges with respect to using higher bleaching chemicals in that. So these are the process side kind of challenges we may get. From the environmental side of challenges, when we use white liquor, which is a combination of sodium caustic, sodium hydroxide, sodium sulfide kind of things, when it gets converted into black liquor, which mainly has all the extracted material from the wood, unwanted extracted material from the wood, including the lignin fragments, including the fatty components from the wood. So in that process, it contributes like in the COD, BOD, TDS kind of thing in the black liquor, and the important major concern is like formation of the hydrogen sulfide and the key mercaptans, which generally create a lot of environmental issues in terms of the odor formation. So it means like we need a technology wherein it can address parallelly the two things, the efficient cooking, at the same time reducing the environmental concern in terms of the odor creating gases like mercaptans and hydrogen sulfide. So today I am going to talk on a technology, a bio-based cooking technology, wherein it can enhance the cooking process. At the same time, it can also work on reducing the environmental concerns. So what is this bio-based cooking program, or a technology I am going to talk today? It's a multifunctional kind of program or a technology which can at the same time tackle with the improvement of the impregnation of the cooking liquor in the wood chips, which is something a very tricky and difficult part in the cooking process, why we use very high temperature and pressure kind of reactors. How it will have focus on reducing the cooking liquor quantity by better impregnation in the wood chips, reducing the mercaptans and H2S which gets eventually formed in the process, reducing from the environmental, so also reducing the odor kind of thing and associated concerns or problems, health related issues with the employees working in the mill. It will have effective, like it has effective methylation properties, so definitely the pulp which is going ahead for the ODL or the bleaching stages, wherein it can create problems, so that effective methylation will also help in reducing the bleaching chemicals in the process. This cooking enhancer technology will also have improvement in terms of like COD, BOD reduction from the process. It improves on the process issues such as like pith or pitch with the technology, and which ultimately like overall contributes in having a good productivity in the system. So what is the technology? It's a dual technology platform, because we need to address two issues simultaneously in the process. One is like having a better efficiency in the pulping process, at the same time also addressing the environmental concerns associated with the mercaptans or hydrogen sulfide formation in the process. So we talk about a technology wherein we are using like a probiotic product platform to reduce the environmental, to lower down the environmental concerns in the process. It's a fermentation product with live probiotic bacteria into it. That is the key technology part, I can say that like here. It has a specially designed consortium which can also handle the sulfurous compound and metabolize the sulfurous compound in the processes. It has special bacteria which can uses the sulfur metabolizing species into it. So it's a technology with a probiotic consortium containing all these different microorganisms. At the same time, the microbes produce in terms the metabolites. These metabolites, they are fermentation produced metabolites, which works very well as the biodispersant. So the combination of the probiotics and the metabolites produced by them can work as an efficient cooking enhancement program, simultaneously addressing two things at a time: the cooking process, the pulping process, and at the same time the environmental concerns associated with it. We'll try to explain the chemistry behind the each and every, like what probiotics in this technology, what probiotics delivers, and what the biodispersant portion tackles about. So combination can work well as the processes are synchronized, like they are intertangled into each other. So a combination technology will deliver result in most efficient way, rather than using a single technology at the or a single interactions at the same time. So biodispersant chemistry very much required. It enhances the capillary action, which is something very much important in the cooking process. Wood chips, as if we all are aware, like penetrating the white liquor in the wood chips is something a very difficult part, and that is why the cooking process are so tedious. So there's something what we require is a better capillary action or a mechanism wherein the white liquor can enter and penetrate inside the wood pores, and that is how where it has actually has a role of breaking down all the lignin kind of fragments into it. So it reduces, yes. So this fermentation generated product has a lot of combination of biodispersant into it, which has a ability to reduce the surface tension and the interfacial tension both. So it facilitates the easy transportation of the active alkali inside the wood chips and makes it more efficient in terms of the chemical interactions. That is how it has the ability to reduce the active alkali consumption. So the X quantity of active alkali which is required for a cooking process, if efficiently it gets delivered at the site where it has the chemical interaction to happen, then yes, the active alkali can be reduced at the same time, which ultimately enhances the delignification process or efficiency. And considering the overall nature of the product, it has the high biodegradability. So ultimately the final COD or BOD, what we talk generally in terms of the chemical contribution, that also get addressed with this chemistry. We talk about like what are the other interactions having into it. So delignification, efficient delignification. So why it, where it helps in having a better delignification also. So as we all aware, like delignification is kind of thing which is generally happen by the combination of NaOH and NaSH. Eventually the hydroxyl and the sulfide kind of ions, which are contributed for breaking down the complete lignin into the fragments. So something along with that, if having a kind of oxidation mechanism which will have a better oxidation or breakup of lignin and make it into a very small fragment so that it can be washed out easily will also help in the process. So the technology also talks about generating in situ peroxide ions in the process. So these are the fermentation generated bioorganic acid. At alkaline conditions, generally they get transformed to the peroxides, organic peroxide through the aldehyde, active aldehyde formation. So this in situ generated organic peroxide, they worked as a bio-based source for oxidizing agent. Since this chemistry generally gets happen inside the active pores of the wood chips, it efficiently helps in also breaking down the lignin, oxidizing lignin further, which generally gets happen at the ODL stage otherwise. So some of the ODL efficiency also gets improved or enhanced because of this. It lowers the active alkali consumption because of that, and also helps in the better lignin degradation into smaller fragments, and its removal becomes easy in that course. The next portion of the probiotics is like having a consortium itself, the microorganisms which are capable of having their own metabolism for the sulfur. So as you are aware, like in case of cooking, all these mercaptans, methyl mercaptan or dimethyl sulfide or dimethyl disulfide formation is mainly happening because of the origin, like the sulfur, the sodium sulfide kind of form what we are using, and the eventual degradation of lignin generally gets form all these components in the process. But cooking process itself has its own cyclic process wherein sulfur gets generated, episulfides get generated, finally those gets converted into like, so these are unavoidable, there are side reactions happening in the cooking process itself which generally land up in the formation of H2S or methyl mercaptans or dimethyl sulfide kind of thing. So the process has, the microbes has, the species of organism has an ability to convert all this sulfide, especially the hydrogen sulfide and the mercaptans, into the back into the molecular sulfur kind of thing, which eventually gets converted into sulfates. So that is one of the thing, like whenever we have done the lab trials or whenever we have done the external validation from like Avanta kind of lab, and when we have done the actual process trials, we have seen almost 50-60% reduction in the mercaptans gases. Not only that, on the like quantifiable levels, but also on the order level, there is substantial reduction in the order because of the probiotic sequestering mechanism, what is happening there. The overall consortium, the probiotic consortium is mainly it's a probiotic consortium, so it has ability to produce a lot of organic acids into it, hydroxy acids and other organic acid in combination. All these acids have capability of multi-chelation kind of thing. So one of the important part, so as a product or as a technology, it can deliver a lot of things at the same time. Since it's a fermentation and natural kind of product and a technology, the microbes and the associated metabolites, what it generates in the process, they have multiple effects simultaneously. So what these different chemistries what I'm talking about is coming from a single product, like the microbes and its metabolites forming during the fermentation process. So this is one of the important parameter, like these organic acids are capable of sequestering the metal ions. So they have capability to like quench the iron, manganese, copper, calcium kind of ions into it. So they act as they play a role as a biochelating kind of agents, which is something important. These are the key metal ions which generally disturb the next level efficiencies. So when pulp carries along with it all these ions, basically these ions has their own interference at the next levels like ODL or at the EOP kind of, especially the alkaline stages wherein we use hydrogen peroxide or alkali kind of chemicals. The interference of this reduces the efficiency or they degrade the peroxide kind of thing. Eventually the active peroxide available for the process gets down. So arresting all these metal ions kind of thing or reducing their levels in the beginning in the cooking level is also important, which gets tackled by the microorganisms and eventually the acids produced by these microorganisms. One of the important part in this technology is ability of this biosurfactant. They work in a multiple way. So since they are the biological kind of surfactant produced in the process itself, they have the ability to form the micelles. At the same time, they have the ability to give the good dispersion also. So in cases of forming like in cases where there are like stickies kind of thing or pith or pitch kind of issues, so definitely it cannot 100% eliminate the thing, but potentially at the cooking level itself, it has the ability to catch all those things and make it take it towards more water solubility kind of thing, wherein this can be efficiently washed out along with the water stream in the beginning stage itself. So carryover should be less in that case. I will just present here some of the results actually what we have when we experimented this on the lab level, and also validated at the second and third level kind of thing. So in the beginning when we study all those interactions at the lab level, so since it's a dual kind of technology, wherein I have to use the probiotic live microbes at the same time the metabolite formed through the microbes. So what should be the ideal combination, like what we should take more or what we should take less? In that condition, we did a study like wherein we have varied the concentration of the biodispersant and the microbes, live microbes. So we did study like we took 50-50% of both the combination, we took 60-40, 65, 70, 75 eventually, trying to increase the biodispersant concentration and decreasing the probiotics, because biodispersant has one of important role of impregnation of the active alkali also. So at increasing order of biodispersant and decreasing order of probiotics, we have checked the results, and what we observed is when we have did this lab experiment in a cooking digester, lab level digester, the 60% of biodispersant in combination with 40% of the probiotics live microbial cells has delivered us better results. Better result in terms of what? Like better result in terms of the screen yield, in terms of the rejects, in terms of the having the brightness, in terms of the kappa number. So since it's a lab studies, we also wanted to validate lab studies on a similar level. So we did some trial through Avanta lab. So we gave them the product and we gave them the similar condition what we have done in the lab and tried to replicate at that level. And even when we did the experiment there, here we have taken the combination of like even using low biodispersant as low as 20% and low probiotics as low as 20% here. So combination, three combination, 20-80 of the biodispersant to probiotics till 80% of the biodispersant and 20% of the probiotics. So in all this combination also what we have observed is the 50-50% combination, which is close to our lab studies of 60% dispersant and 40% of probiotics. So similar, this 50-50% combination has given optimal result over here in terms of forming the lesser rejects, better kappa number and higher brightness. Also one of the important thing what we have observed here is if we see the blank has like a stress concentration of almost 598-600 ppm into it, where there was no cooking enhancer program or no mercaptans quenching kind of thing, chemicals was used over there. But if you see the set 1, set 2 or set 3, in either cases, the mercaptans and H2S, like H2S has substantially reduced from the 600 to 270 or 362 kind of level. So there is the trials has achieved almost 40% or 50% of hydrogen sulfide reduction in the process, and which was also observed in the case of the order reduction in overall process. So after all this lab studies and the external validation, we wanted to have actual feel of the process. So one of the mill which is very they are using the technologies already. So we have approached the mill and we actually tried to experience the chemical interactions what we are trying to see in this product at the lab level studies and at the external validation level. So we did the case study as a case study in a mill where it is almost 400 ton per day kind of pulp production. And here also the important thing over here, like we use 60% as the optimum concentration what we got in the lab studies. We tried to use 60% of biodispersant along with 40% of the microbial portion, probiotics over here. The important thing what we have achieved over here is we could see, because lab level sometimes some points are difficult to see, very small digester, and you could not get all the data like what you actually get at the magnified level when you do the actual application in the field trials. So here in this case, the regular active alkali consumption in a process was 18.4%. So when the probiotics and this biodispersion 60-40 combination was used over there, the process with the same efficiency could happen at 17.4% of active alkali. So there was almost 1% of active alkali reduction in the process, even at the lesser DCM extractives. So the concept or the chemistry what I was talking about, the probiotics along with its metabolite has the ability of taking out the extractives also from the material. So if you see the conventional process happening had almost DCM extractives of 0.13, but it was further reduced even at 1% of active alkali like reduction. The extractives has not increased in the process. And the another important point, the brightness improvement at the P2 stage. If we see the conventional and compared it with the probiotic technology at the 18.4 active alkali and the 17.4, the P2 brightness gain was much higher as compared to the conventional process also, and even at the higher active alkali consumption in presence of probiotics. So where it was almost brightness has come to 44. So that was something very good gain, and it was something a kind of good validation also for us as a technology to understand like the deliverables what it is giving as a technology, the probiotics and biodispersion combination at this typical 60% and 40% can do, like what are the unique benefits of this. So in terms of technology benefit, if we see, it can be used at broad spectrum of pH and temperature. Generally when microbes we consider, we think microbes cannot survive at certain high temperature. But the consortium has some unique features where this, especially the sulfur sequestering bacteria, they are high temperature, they are thermophile bacteria, and they can even survive about 200 to 50 degrees centigrade temperature. That is how they even metabolize the sulfur mechanism at that temperature at the cooking level where the temperatures are very high. They can be stored at very ambient temperature. So no, generally when somebody thinks about probiotic technology, how it will, or a microbial, live microbial technology, how it will get scalable. So that is the technology part wherein microbes can be stabilized even to store, because every like milk cannot store a microbe kind of thing at a temperature condition what is recommended for that. But a technology when gets like a consortium when gets make the kind of preparation of consortium does not require a really storage condition. They can be stored at room temperature, or they can be even stored at little bit higher temperature, 50 degree or 60 degree. Microbes won't affect in terms of their efficiency or working metabolism. And other important thing is, this is something kind of a technology which can be used over not only wood chips, but it can be used also in case of the agro waste and bagasse kind of thing. In fact, in bagasse kind of thing, where generally there will be a problem, a storage kind of issues, wherein there will be a reduction in the yield also on the longer storage, a probiotic kind of technology, when it gets spreaded on a bagasse kind of furnish, especially the microbial degradation which is going to happen in bagasse kind of thing gets arrested because of the gram positive probiotics kind of microorganisms. So in bagasse kind of thing, it may have certain other effects also apart from what we could see always in the wood chips. So in a way, like a biological technology or a probiotics or a biodegradable kind of technology have multiple effects at the same time when they deliver or focus on one single aspect of the process. In terms of environmental benefits, if we see, the product as a live microorganism itself has the ability of controlling lot of biofilms and slime formation in the process. So whenever kind of microbes get entered in the process, these probiotic microbes, they have ability to get multiply in the system. So when they get multiply in the system, they also takes care about the biofilms or the slime formation which is getting happened in the system if the problems are there. Definitely what we discuss is the mechanism. They have capability of reducing the mercaptans and hydrogen sulfide formation in the process. That is how the order, which is the main concern for the environment also, gets almost 40-50% reduced when this probiotics is in the usage. There are no more toxic chemicals, so when they get used in the process, in fact, they don't contribute by themselves in as a COD or BOD kind of thing. In fact, they try to reduce the COD BOD content of the process. So that is how somehow the biological technology helps in reducing the overall environmental load in the processes. Apart from that, when we talk about the process kind of benefits, so kind of technology like probiotics, biodispersant, as we have seen in the results also, they have helped in reducing the active alkali consumption in the process, almost by 5 to 7% in the process. And not only that, enhancing while using a technology at the cooking level, if certain technology can also help at the same time making the next stages of bleaching, including the ODL step, more efficient, yes, then kind of technologies will also give better benefits, not only in terms of the process efficiency side, but also from the environmental side by reducing the chemical loads at both the acid and alkaline stage. So they make the process more and more efficient at the beginning itself. Like. So probiotics, I can just say that like when I work on a probiotics kind of technologies, making different consortiums or making a product which can have a potential to replace or to work more efficiently or to take more towards green environment or making the processes more cleaner and better. So this is a kind of technology, a step towards the sustainability, I can say that. By it has the ability of reducing or eliminating these hazardous chemicals getting used, creating the environmental concerns in terms of order, and having the better utilization of water kind of resources by lowering the COD, BOD kind of thing from the water. So it can be a step or a step towards like making mills or facilitating mills more towards like having reducing this climate change kind of thing what we're talking in the near future now, taking to more towards a green certification kind of thing and reducing really the carbon footprints. Thank you.